I'll be presenting evidence that the Earth's surface was shaped by retreating floodwaters, forming features that cannot be explained by uniformitarian scientists. I will first deal with how the floodwaters ran off the continents and the great erosion that occurred during this runoff. Then I will examine the character of that erosion by analyzing two landforms, as we call it in geomorphology, carved during the sheet flow phase of the retreating stage. One hears such statements as this from many sources, both outside and inside the church. This is from Davis Young, a retired professor of geology at Calvin College. In the book euphemistically titled The Biblical Flood, he says, "There is no geological evidence to confirm the idea of a universal deluge." How should we respond to such challenges? Well, I apply 1 Thessalonians 5:21. That's my theme verse for research. Examine everything carefully, hold fast to that which is good. I'm going to hold fast to the Bible as God's revealed word to us and to Jesus as my Lord and Savior. Then I'm going to examine the data as carefully as possible. And that's what I've been doing. There really is a wealth of evidence for the flood when I've done this. Once you take off your uniformitarian glasses and you put on your flood glasses. Uniformitarianism is the idea that slow processes occurred over millions of years, forming everything. I'll be speaking of a whole genre of evidences on the surface of the earth in the field of geomorphology. Geo means earth, morphology means shape. It deals with the shape of the earth, and this is what I'll be dealing with. And they also call them landforms, the form of the land. Landform can be a valley, a mountain, a water gap, a planation surface. I'll be using Taz Walker's classification of the flood because he uses just the Bible to determine stages and phases of the flood without regard to any secular ideas like the geological column. I'll focus on the last half of the flood, the retreating stage with its two phases. Number 4 is what I call the sheet flow phase. That's where just after the peak of the flood, there's no mountains to obstruct the flow. You had wide currents, maybe 1,000 miles wide and maybe 2 miles deep, moving across the earth. And if you look down current, it looked like a sheet, very thin and wide. So it's sheet flow is what we call it. Number 5 is the channelized flow phase, when more mountains and plateaus extend above the floodwaters. It forces the water to go around these objects, creating different landforms superimposed on the sheet flow landforms. Now, this is the erosion by climate and surface topography in a total of 5,000 years based on present processes. For instance, these are big, broad-scale averages. It doesn't include landslide areas, places glaciated. Anyway, you can see from that areas of high precipitation and mountainous have an average of 7 feet of erosion in the last 5,000 years. Now, of course, if you add the ice age to that and heavier precipitation, you might triple this, for instance. But what this tells us is that there has been not enough time for erosion since the time of the flood to erase the evidence of flood runoff, if the flood was a real event. You should see the evidence of the flood runoff, because erosion has not erased it. Before we get to the geomorphological evidence, we will answer 2 questions. First, how did the floodwaters drain off the future continents? I believe the answer is right in the Bible. Psalm 104, 6-9. You covered it, that's the earth, with the deep, as with a garment. The waters were standing above the mountains. At your rebuke they fled. At the sound of your thunder they hurried away. Notice I've emphasized the word covered. The mountains rose, the valley sank down to the place which you established for them. You set a boundary that they may not pass over, so that they will not return to cover the earth. I've emphasized the last phrase here. There were only 2 times when the earth was totally covered with water, during day 2 and 3 of creation and during the flood. Now, the word covered in verse 6 is what the flood would do, while in day 3, the dry land was uncovered. Also, verse 9 indicates the shoreline was set so that the water will not return to cover the earth. So Psalm 104, 6-9 must refer to the flood. Notice verse 8. the mountains rose and the valley sank down. I believe that's the correct translation from the New American Standard Bible versus other Bibles that's talked about the waters flowing up and over, because God set a place for the waters. They drained already. So this is a better translation, I believe. The mountains rose, the valley sank down. So when that happens, the water drains. If everything is generally even and land goes up and land goes down, the floodwaters drain. Here's the big picture on day 150, which I believe is the peak of the flood. There was a general west to east sheet flow in the western United States based on paleocurrent direction indicators in the sedimentary rocks and the early transport of resistant rocks from the western Rockies clear way out into the high plains. The currents were wide and there were very few obstructions to flow, and the upper crust and capping sediments were generally horizontal. They might have been bumpy like this, but the upper crust is granite, and it probably had thick sedimentary rocks before the uplift. And then everything started to uplift, and the waters drained, and in the western United States, it split the current with that on the east side moving east, and that on the west side moving west into the Pacific Ocean. Is there evidence that the mountains rose and the valley sank down? Yes, all over the earth. The state of Wyoming consists of high mountain ranges and generally flat basins filled with sedimentary rocks caused by tremendous differential vertical tectonics. For instance, here, the Wind River Mountains, right there. I was just over there in that area last week. The Hanna Basin, I'm going to be pointing these out a little later because they're very significant. Let's take a cross-section from the Beartooth Mountains right there through the northern Bighorn Basin to the Bighorn Mountains. This is the granite pattern is these diagonal lines. That's the granite of the upper crust in the Beartooth and Bighorns. And they're about 13,000 feet above sea level with a few erosional remnants of the strata that used to lie over the granite, like right there, Beartooth Butte. And in the Bighorn Basin, the granite is 10,000 feet below sea level in the northern Bighorn Basin and 20,000 feet below sea level in the southern Bighorn Basin. So it's filled with about 15,000 feet of sediments, of which the top has been eroded off. I calculated about 3,500 feet of erosion over the top of the Bighorn Basin based on erosional remnants like Tapman Mountain in the middle of the Bighorn Basin. So the main change here is at the Beartooth Fault, where it went up 23,000 feet or down like this, differential vertical tectonics. And it had to happen underwater because the Bighorn Basin filled with sediments in this process. And there's other evidence that this around this area that this area was deep underwater for a while. Now, the other areas of Wyoming show more differential, even more differential vertical tectonics. For instance, I mentioned the Wind River Mountains and the Hanna Basin. Well, the Wind River Mountains is the upper crust of granite that's now 14,000 feet above sea level. And on the right, you'll see some of where the granite is below the base, in the basins below the sedimentary rock. The Hanna Basin, the granite, based on seismic methods, sometimes they can drill down to the granite, but it's too deep in these basins. They generally do seismic methods. In the Hanna Basin, that little basin, the granite is 31,000 feet below sea level. So if it was generally even at day 150, we had 45,000 feet of differential vertical tectonics in the state of Wyoming. And yet they challenge us of how can the floodwaters cover Mount Everest? Well, actually, that's a wrong challenge because Mount Everest and the Himalayas actually rose up out of the floodwaters. We have marine fossils on the top of Mount Everest, by the way, as well as most mountain ranges of the world. I believe this differential vertical tectonics also occurred at the large scale of continents and ocean basins. At day 150, the continents were starting to rise and the ocean basin sinking. There's plenty of evidence that the water ran off the continents during uplift, as I will show. But is there evidence that the ocean basins have sunk? Yes, there is. One piece of evidence, and there are others, is guyotes, flat-top volcanic seamounts or underwater plateaus. Many of these seamounts formed as hot spots or hot lines during the flood, and guyouts were playing generally close to sea level. But guyouts now are an average of 5,000 feet below sea level, indicating the bottom of the ocean has sunk. My favorite secular geomorphologist, Dr. Lester King from the University of Natal in South Africa, says this about guyouts. Marine volcanic islands which have been truncated by the waves and since subsided below sea level are called guyouts. Most of them seem to have sunk by 600 to 2,000 meters, translated 1,960 to 6,600 feet, and it is evidence that they afford a measure of the amount by which the ocean floor has sunk in later geological time. The Pacific floor especially has subsided. All ocean basins afford evidence of subsidence amounting to hundreds and even thousands of meters in areas far from land. So guyouts are strong evidence for the ocean basin sinking. Lester King goes on to say that differential vertical tectonics is obvious all over the earth, everywhere, even on the ocean bottom. Notice the adjectives he uses. So the fundamental tectonic movement of global geology are vertical. Notice that, fundamental, global geology. Up or down, every part of the globe on the continents or in the ocean basins provide direct geological evidence that formerly it stood at different levels, up or down. What he's saying is that everywhere you see the evidence that it's gone up or it's gone down, even on the bottom of the ocean. 80% of the ocean bottoms is abyssal hills. These are faults in the basalt where part's gone up and part's gone down. A lot of it's covered by sediments, but the seismic methods show these. So you see this tendency all over the earth of differential vertical tectonics. He goes on to indirectly quote Psalm 104:8. He says, there have been repeated tectonic episodes. He's talking about vertical tectonics, always in the same sense. The land goes up, the sea floor goes down. Isn't that powerful evidence for Psalm 104:8? In summary, there is tremendous evidence all over the earth for differential vertical tectonics to drain the floodwaters. The second question I want to answer is there evidence for huge erosion on the continents as they were coming up out of the floodwaters? Yes, it is abundant on all the continents. Here's the Colorado Plateau. It's 132,000 square miles. It is color-coded for altitude, with blues being lower elevations and greens and browns being higher elevations. Note the San Rafael Swell right here. The San Rafael Swell in the northwest Colorado Plateau is an eroded dome or anticline where the strata went up like that. It covers 3,000 square miles. Based on the dip of the strata on the north limb, right there, I did a trigonometric calculation of the amount of erosion over Price, Utah. These numbers will surprise you as they did me. This is what I found from the dip of the strata. It dips about 8 degrees, but I was more conservative. I made it 6 to 8 degrees. And then the question marks on the dashed lines are there because I assumed the same thickness going up over the San Rafael Swell. This is a north-south cross-section here. I assumed that the strata was the same thickness. I calculated there was 4,200 to 5,100 meters, or 14,000 to 17,000 feet of rock was eroded over Price, Utah, of which the top formation is the Green River Formation. This is just one method of figuring out the erosion in an area, and I've been concentrating on this for the last few years, and it is tremendous, the amount of erosion on the continents. I mentioned at the field trip a little bit about the erosion in the Appalachian area. In fact, the San Rafael Swell represents a good average of erosion for the whole Colorado Plateau, as said by Schmidt in the geomorphological journal called Earth's Surface Processes and Landforms. He says, taken overall, the mean thickness of sedimentary cover removed from the Colorado Plateau lies between 2,500 and 5,000 meters. That's the average erosion over the Colorado Plateau. And there you can calculate it because you have nice domes that have been eroded. Other places you can't do it because we don't have those eroded domes, but I'm sure that a lot of other places have had just as much erosion, if not more. And here's a few that I found from the literature. 6,500 feet, the Rocky Mountains and foothills in southern Canada. 21,000 feet for the Appalachians, of which I verified and has been published in the Creation Research Society Quarterly during the last year. 20,000 feet, Flinders Range, South Australia. 10,000 feet, the Welsh Mountains of the United Kingdom. 5,000 feet, southeast England. 8,000 feet, southern Africa. So the continents have been greatly eroded. I would conservatively estimate that there was an average of 1.5 miles of sediments and sedimentary rocks on the continents at the peak of the flood, and that about 1/2 of a mile on the average was eroded during the retreating stage of the flood, or the recessive stage as Taz Walker calls it, leaving an average of 1 mile left. Now that's an average. There's some areas where it's 10 to 15 miles deep. Some places there's no sedimentary rocks. So 1/2 a mile, I think, is a conservative estimate. This is a summary diagram illustrating the huge continental erosion and how it is related to the flood. This is the current continental surface where you find the fossils and the current depth. But there's evidence that at the peak of the flood, we had a lot more sedimentary rocks and sediments on the continents right up in here that was eroded off during the retreating stage of the flood. Now, the late Roy Holt calls it the Erodozoic. Thought that was a nice twist on the geological names of Paleozoic, Mesozoic, Cenozoic. So this illustrates huge continental erosion. Is it possible that the reason we find few human fossils is because of all the erosion during the retreating stage of the flood? The humans maybe were buried near the top layers, and as we had all this erosion, as the continent came up, they got re-eroded and pulverized in the currents that were flowing off? I think it's quite possible. There's evidence that this erosion occurred rapidly when we examine the character of the erosion. For instance, this is the erosion of a field in South Africa caused by a flash flood. Notice the erosional remnants left behind. Right in there. So floods, especially flash floods, leave erosional remnants. Also during the Lake Missoula flood, that 2,000-foot deep lake in the valleys of western Montana burst through the ice and flooded through eastern Washington. It left some erosional remnants also. So erosional remnants are evidence of rapid erosion, not millions of years of erosion. Otherwise, these erosional remnants would erode with the rest of the erosion. And there's thousands of these erosional remnants. The best one is Devil's Tower. Now, Devil's Tower is about 1,200 feet above the flat plains, and it's about 1,000 feet wide. And it's very likely the conduit or the throat of a volcano where the lava was coming up into a big volcano erupting well above it. Now, conduits of volcanoes don't erupt in air. They erupt in sediments. You have to have some hard rock around that to form that. So this implies the sedimentary rocks were up to at least the top of Devil's Tower. In fact, the uniformitarian geologists think it was way above Devil's Tower, and I believe them. I think it was. They will tell you that at Devil's Tower National Monument, that the plains erosion took millions of years. One sign used to say that the Devil's Tower, that the plains erosion took 40 million years, but Devil's Tower never decreased in size in all that 40 million years. The new sign says 2 million years. They're getting a little closer. Now, when you go to national parks, you'll see things like this. And think erosion. You need to put on your baloney detectors, as Philip Johnson says. And you'll see inconsistencies in their story, like the walls of Grand Canyon represent strata that's 300 million years of deposition. Well, at that rate, you should see canyons and valleys all through there because modern day erosion is so fast, you can erode all of North America down to sea level in a minimum of 10 million years, but there's other processes going on, so a maximum of 33 million. So erosion in a million-year timescale is fast. So you should see canyons and valleys there. So when you go to Grand Canyon and other places and they tell you all those millions of years, look for the erosion in there. You don't see the erosion between the layers. It is at Devil's Tower, it's made up of joints, is what they called, cracks that fill with water, and there's a lot of freeze-thaw weathering. So freeze-thaw weathering should knock this to a pile of rubble in a very short time. I'm giving it a few tens of thousands of years at the most that it should be there. And vertical cliffs and faces erode a lot faster than horizontal surfaces. So there's no way Devil's Tower is going to hang vertical like that, 1,200 feet, while all the plain strata erode all around it. This is strong evidence that it had to be eroded rapidly. So if uniformitarianism were true, Devil's Tower should change over millions of years of plains erosion like the following. After millions of years of erosion, let's say at the end, at this stage, there was just the top showing. So the next layer or two erodes, and that's what you should get. Just a pile of debris or rubble at the best. And then when you finally get down there, that's what you should expect over millions of years of erosion. But during the flood, here's what you'd expect, I would expect during rapid flood erosion. A big volcano was going off and probably broke through the surface, spreading ash. We have a lot of ash layers, which by definition means that it is volcanism that moved up into the air and spread. So a lot of times these volcanoes build up and spread above the floodwaters. So a volcano was going off, and then it stopped, and the floodwaters sheared off the top, strong flow, and for some reason Devil's Tower hardened a little more than the sedimentary rocks, or maybe the currents weren't quite as strong. I don't know exactly the reason for this, but it had to happen rapidly or Devil's Tower would not be there. You know, as it continues, strong flow, erodes the sedimentary rocks. Finally, that's what you see. A vertical tower, 1,200 feet tall and 1,000 feet wide. So the tower not only shows that the erosion was rapid, but also that it eroded not that long ago, because its width of 1,000 feet has changed little, and there's relatively little talus at the base of Devil's Tower. And by the way, observers who have lived there for a while hear rocks crashing down fairly regularly. So it's eroding today. So I believe Devil's Tower is an icon for rapid flood erosion and thousands of feet of flood erosion. There are many other tall erosional remnants across the earth, such as Monument Valley. These are about 1,000 feet tall. They're capped by sandstone. That sandstone is not very hard. You can go up there and rub it off. It's not cemented that hard. So there's no way that you're going to erode all this material through this valley and leave these erosional remnants vertical like this for millions of years. It's evidence of rapid erosion, leaving behind erosional remnants like that flash flood in South Africa. This is Shiprock in northwest New Mexico. It is 1,700 feet above the flat bottom floor. It is also the conduit of a volcano, so the sedimentary rocks had to be well above the top of Shiprock. So in another sign of tremendous erosion in northwest New Mexico. So tall erosional remnants show that the huge erosion of the continents was rapid, just as expected during the retreating stage of the flood. Then the question presents itself, where did the sediments go from all the sheet erosion of the continents? You would expect sheet deposition somewhere. Indeed, there's a sheet depositional area along the edge of the continents, which subsided deeply during the flood. There's evidence that, like the East Coast went down about 8 miles, while this area around here went up. 8 miles. This is in the uniformitarian literature. Why? Because we have some deep cracks, 200,000 square miles in area, 18 kilometers deep right off the East Coast that are filled with sediments and sedimentary rocks. And this is not unusual along other coasts. So sheet currents coming off the continents would slow in the deep water, and that's where they would drop their load, depositing the sediments, now sedimentary rocks, forming the continental shelf and slope and the rise for areas that have the rise. The profile is very unusual for natural processes of sediment deposition. As Lester King says, here's what he says about the mysterious continental margin. Some of these continental shelves, the average is 50 to 100 miles, but some of them go out 300, 400 miles, and it's really flat, and then a big drop-off. A really unusual profile for natural processes of currents depositing sediments. Lester King says, here's the problem. Briefly, the shelf is too wide, and towards the outer edge, too deep to be controlled by normal wind-generated waves of the ocean surface. So the continental shelf and slope is a mysterious profile within uniformitarian geology. But rapid sheet deposition, as the currents were coming off the of the continents during sheet flow runoff of the continents can explain the continental shelf and slope. Now, a summary. Continental erosional remnants are evidence for rapid sheet erosion. The continental shelves provide evidence for rapid sheet deposition along the edges of the continents, not slow processes over millions of years. So the first sheet flow landform I'm going to talk about are what's called erosion or planation surfaces. An erosion surface is a surface cut in rock, hard rock. It's not a depositional surface, it's cut in hard rock, and it's generally left a little rolling. A planation surface is generally flat or nearly flat. And you usually have a thin veneer of rounded rocks on these things. And this is during the sheet flow phase, right in here. Here's a definition of erosion surface. It's a land surface shaped and subdued by the action of erosion. Not too enlightening, but he keeps on going. Especially by running water. The term is generally applied to a level or nearly level surface. Why running water? Because you have all those rounded rocks. You have many rounded rocks in these planation surfaces. I've seen dozens of planation surfaces. Many of them, not all, have rounded rocks. You round rocks by water action. In fact, it's well known in geomorphology that the landscape we see on the continents has been shaped by water. Do we know a mechanism that can do that? Okay, let's take a look at one. I took this picture just last 2 weeks ago in the Northern Bighorn Basin. The Northern Bighorn Basin is generally a planation surface capped by rounded rocks, some of which are quartzites that don't outcrop anywhere in Wyoming. They've come from central Idaho, as I'll talk about. But and they've been dissected a little bit by erosion after they were formed. You can see the dip of the sedimentary rocks to the west at a pretty steep angle, from anywhere from 30 to 60 degrees. And usually basin-fill sedimentary rocks and plain sedimentary rocks are a combination of hard and soft rocks. And whatever planed off hard and soft rocks the same. And this has rounded rocks, so it's water that did it. And by the way, planation surfaces aren't forming today, but I'm getting ahead of myself. So this is an example of a planation surface right here, just a remnant of it. Planation surfaces were once much larger, as Lester King says. Lester King was a world traveler, so he has a whole book on these topics published in 1967. And he talks about these. A planation of extraordinary smoothness, in other words, very flat, developed over enormous areas in all the continents. From it, most of the world's present scenery has subsequently been carved by renewed erosion. In other words, once the planation surface formed, and I believe by fast, powerful currents, there was channelized erosion, which I believe was later in the flood, and it dissected a lot of these planation surfaces, so that now we just have remnants around. Planation surfaces once covered much of the current continents. In fact, Africa is considered 60% a planation surface called the African surface, which I published an article in the Journal of Creation, a couple issues ago on that topic. But they've been reduced in size by erosion, by differential vertical tectonics also. Now, this is the area where I live. This is northern Montana, the high plains, and adjacent Alberta and Saskatchewan. And on the high plains, we generally have 4 levels of planation surfaces. It's a generalization because I have found exceptions to this. The highest level is called the Cypress Hills, right in here. It used to be continuous. It's look at the scale. This is a large scale. Here's the Cypress Hills. It was probably continuous, about 80 miles long, 15 miles wide, over 1,000 square miles. And I believe it was dissected probably late in the flood by channelized erosion or by the ice age afterwards that caused erosion on it. Anyway, the Cypress Hills is the highest level of planation surfaces. The second is the Flaxville Plateaus. I was just up in this area 3 weeks ago, right in this green area right here, and then there's some remnants just east of Glacier Park. And these are all capped by quartzite rocks, which I'll talk about. The Cypress Hills is capped by 75 feet of rounded quartzite rocks. I'll tell you what quartzite is. It's a metamorphic sandstone. I might as well tell you right now. Also, notice the rose diagram. We have paleocurrent directional indicators in the gravels. By gravels, I mean gravel size, cobbles, and boulder size. And that's a rose diagram that indicates that they came from the west-southwest, indicating transport from the west-southwest. I will deal with the quartzites later. But here's a picture of the northwest Cypress Hills. Notice how really flat it is. It's 4,800 feet above sea level there. It's a high plateau, 2,500 feet above the rivers to the south and north. So it's really sticking up there. And it's just an erosional remnant. It's an indication that this surface probably extended hundreds of miles in a north-south direction and probably tens of miles in an east-west direction before it got eroded all around down to the next planation surface, leaving it as an erosional remnant. Now here it is in the central Cypress Hills. I have found erratic boulders from the Ice Age in this valley, so I believe this is probably eroded during the Ice Age. And when you get to the eastern Cypress Hills, there it is near East End, Saskatchewan. Notice how flat it is. And when you drive up to the top of it, it's flat as a pancake. And you're driving on 75 feet average of rounded quartzite rocks, which when you drive to the edge of the plateau and you look north down into Canada, 1,000 feet below, you're starting to see what capping it. It's conglomerate, cemented quartzite rocks. And that's what it looks like right there. It's about 95% or more quartzites, which I'll talk about soon. And I've noticed a lot of them are iron stained on the outside. But that's what the Cypress Hills planation surface looks like. The quartzite boulders, this is a quartzite boulder from the Cypress Hills. And by the way, quartzite's one of the hardest rocks in the world, and yet they have these percussion marks on it, semicircular cracks. And the only way you can do that is by ferocious, turbulent pounding during high-speed flow. And I'll give you some, in fact, this is the big picture right here. So the planation surface was formed by the larger rocks. I mean, it's moving at high rate speed, the water was, that is, and the larger rocks were moved along the bottom and was eroding, scraping the bottom, eroding it to a flat surface, while the small to medium size were carried up in turbulent flow and come crashing down. So that's the big picture, a current coming off the Rockies, wide current, because it was a sheet flow at one time, depositing on the Cypress Hills planation surface that was once more extensive. Now there's a relationship between the horizontal velocity and the fall velocity for the maximum size rock carried up into suspension for a while. This gives us a minimum estimate of the current speed and depth. Now Peter Kleberg used this relationship, and this is what he found, and it's based on the shape of the rock too, and as well as the fall velocity. So you had to use some calculus in this calculation. So the maximum rocks that he believed was carried up in suspension was a bullet-shaped rock about 6 inches in diameter. And so based on that, the relationship between the horizontal and the fall velocity, he got these minimum current speeds. Now just look at the bottom one, of 65 miles an hour and a minimum depth of 180 feet. What does this indicate? 65 miles an hour is 2 to 3 times the speed of the fastest flash floods on Earth that come crashing down steep mountain slopes. It all adds up to wide, powerful currents sweeping across the western Rockies and eroding the high plains strata down to a series of planation surfaces at various levels. The Cypress Hills, like I said, is the highest, and it's well above the lowest one, which is the fourth level down. Powerful evidence for the runoff of the floodwaters. Now, planation surfaces are global. In fact, in Antarctica, you see a lot of mountains sticking up above the ice, and a lot of them are plain flat. See, a lot of these planation surfaces are at the tops of mountains. For instance, these are the Beartooth Mountains, which I showed you a profile of the Beartooth Mountains not too long ago. And they're flat top. In fact, the whole Beartooth Mountains is one planation surface that has been faulted up at various elevations and also eroded and dissected into deep canyons. For instance, this level, about 10 to 11,000 feet, is an eroded planation surface, but up here, it's hardly eroded at all. Notice how flat that is. That's granite or gneiss. You know, nature is not forming flat surfaces in granite and gneiss today. It takes a powerful current to shear off granite to a flat surface. And you can see the faulting. Here's a little bit of fault that lowered this. So a lot of faulting has broken this up some. Also, the northern Wind River. Actually, all the Wind River mountains are flat top. This is Square Top Mountain and 11,500 feet in the Wind River Mountains. Now, the tops of these granitic mountains, which represent the upper crust, could represent what's called exhumed surfaces, or the great unconformity as seen in the Grand Canyon, which was formed early in the flood by powerful currents. But there's other indications around here that this probably, I don't want to be dogmatic about it, but probably formed during late flood runoff because there are other mountains. See, when the Wind River Mountains rose up, the strata a lot of times tilted along the edge. And that tilted strata was planed also. And here is Gypsum Mountain, 11,500 feet. And the snow has made it so that we can see the dip of the strata west about 40 degrees, and it's been sheared off flat. And that's not part of the great unconformity. So it's looking like the top of the Beartooth and the top of the Wind River Mountains and maybe a lot of the Rocky Mountains are flat top, by the way. That maybe this occurred late in the flood and not early in the flood. I can't be dogmatic about it, but here's some more planation surfaces around Grand Canyon. This is the Grand Canyon area. Do you know that there was about 12,000 feet of strata above Grand Canyon at one time in the whole area that got eroded off as a sheet, leaving the Grand Staircase to the north? And before Grand Canyon was even cut, forming a planation surface. Here's a planation surface in eastern Australia, the tableland. It's about 3,000 to 4,000 feet. And this is vertical strata right here, and it's been planed off. But it's kind of rolling up there, so it's more of an erosion surface. Well, how does that happen? Nature doesn't do things like that today. What does this mean? Well, we probably had a big, huge fold in the strata like this, and then the floodwater just sheared off like that, leaving the vertical strata with a flat surface on top. And around this area right here, this is a picture from the Piedmont. The Piedmont area, which is the area just east of the Blue Ridge, it's approximately, 75 miles wide, and it extends all along the edge of the eastern Appalachians. It's been plain flat. The metamorphic and igneous rocks below that just go like this, tilted at steep angles. And if you would dash those up in the air, they go really high, thousands of feet up like that. It's all been sheared off, flattened by, I believe, the retreating of the floodwaters. Also, on the other side of the Appalachians, you have the Allegheny Plateau. And this is a planation surface that's been eroded flat, but it's been dissected by channelized erosion after the formation of the planation surface by sheet flow. That's forming the valleys. And also, it's roughened the surface. Now, the Cumberland Plateau is probably the best area to see the flatness of what it was originally, because it's pretty flat on the Cumberland Plateau of the southern Allegheny Plateau. Anyway, here's a planation surface in north central Montana. And here is one of the key elements of all this. The most important is that planation surfaces are not forming today. They're being destroyed, except when a river floods and erodes a riverbank, then it'll plane the strata. So planation surfaces are being destroyed by present-day erosion, as you can see in this example here of this stream valley here. But if we use the river as an analogy for the formation of planation surfaces, I mean, we're talking about one gigantic flood to form planation surfaces all over the earth. So we can use that small little area where they're forming today by floods along rivers to extrapolate to the runoff of during the Genesis flood. Here are two summary schematics. And you especially see planation surfaces on dipping sedimentary rocks that are a combination of hard sedimentary rocks and soft. What normally happens with millions of years of erosion, what would happen is the harder rocks would be ridges, and the softer rocks would erode, being filled in with some of the erosional products. This is what you'd expect based on uniformitarian erosion. And we do see these things on the earth. And they can form during the flood by slow currents that don't quite erode all the hard rock. Slow currents will do that, but fast currents will shear everything, both hard and soft rocks, because this is what you often find. Both hard and soft rocks planed the same, leaving a capping of rounded rocks on top. Powerful evidence for the retreating stage of the flood. And it's all over on the surface of the earth. You can drive around and drive up on these things and see these things, especially in the western United States. So in summary, planation surfaces are not forming today, they're being destroyed. They were once much larger. In fact, in a book called On the Origin of Mountains by two geomorphologists, Ollier and Payne, they say that these planation surfaces were huge at one time, and they uplifted to form our mountains only when they eroded the planation surface. That's why they're still at the tops of mountains, because they uplifted and were destroyed by erosion. That can happen in the flood too. They're common as erosional remnants. They're worldwide, difficult to explain by slow processes of erosion over millions of years. This is spectacular evidence for the flood, for the evidence of the retreating stage of the flood. Second sheet flow landform. I'm only going to talk about sheet flow landforms, and I don't have time to go into channelized landforms, which I'd love to do, because you've got a lot of them around this area, like water and wind gaps. But anyway, the second one is quartzite rocks spread hundreds of miles from their source in the northern Rockies. Now, quartzite is a metamorphic sandstone, and it was metamorphosed probably by deep burial. So this is the big picture. West-east currents are eroding quartzites in the western Rockies and moving them down current and whittling them down to smaller size and spreading them long distances. And then as the Rocky Mountains were exposed above the floodwaters, it split the floodwaters with the current continuing east on the east side, and then another current developing and going back towards the Pacific Ocean, which is sinking. Remember, the land's going up, ocean basin sinking, the water is running off, sometimes at high speeds, especially if there's no mountain barriers to slow it down. So this is where the quartzite comes from. I've seen big, thick layers of it, thousands of feet thick. This is what's called the belt supergroup. It's 90% metamorphic shale called argillite and about 10% quartzite, a metamorphic sandstone, very few limestones. It's up to 20 kilometers deep because it's folded, and if you put the folds on end, it's at least 20 kilometers. It's a giant hole that I believe occurred early in the flood. And the quartzite generally outcrops in the western belt formation. The grade of quartzite, now the quartzite I'm talking about is generally high grade. It's been well metamorphosed, and when it metamorphoses, it recrystallizes. See, sandstone is 20 to 25% air. And so when it recrystallizes during metamorphosis, it fills up those pores and becomes a very hard, tough rock. And that's why you find quartzites that are left long distances, because the other types of rocks were pulverized, But anyway, this is generally where they outcrop. Now, there are other smaller locations of quartzite, but that's the general location of them. Anyway, this is where I find them in Washington and Oregon, and I've been to many of these locations. The green triangles represent small areas. The larger circular green areas are larger areas of quartzite. But right in here, these are on top of the Wallowa Mountains of northeast Oregon. The tops of them have lots of quartzites, big ones. I'm going to show you these. I hiked up and found some. This one's on top of the Blue Mountains, north of Burns, Oregon, and there's lots of them on top of the lava ridges around Yakima, up to 4,000 feet above sea level. And they're found clear to the Pacific Ocean and other places. One of the most interesting places is in the Puget Sound area. That area that's shown in the red there, red dash, is glaciated. The glaciers came down and picked up a lot of the quartzites that were in the Puget Sound area. And sure enough, I've examined about 7, 8 locations, and every one of them had rounded quartzites from the nearest source is southeast British Columbia. They were found in the glacial debris. So here's one location on top of the Wallowa Mountains at 8,200 feet near Lookout Mountain. We're camped, or we're standing there and sitting there on a quartzite area. This is the largest quartzite up there. I was hoping to bring that back. We had horses going up there, but that weighs approximately over 400 pounds. Notice how it's polished and rounded by water action. In fact, the current was going so fast that these finer sediments in here, around there, have gold in it. In fact, on the top of the Wallowa Mountains, they mined the quartzite. Placer mined the quartzites because it had gold in it. In fact, on top of the Blue Mountains of northeast Oregon, there's gold in there too. And on east of the Continental Divide in Wyoming, there's gold in the quartzites. So we're talking about powerful currents. And this is the top of the Blue Mountains. It's called Gold Hill, by the way. When we got up there were all kind of pockmarks, like there had been a war there. But people dug for gold in the finer grain material. Now, I showed you this already. Now I'm going to talk about the quartzite that caps these planation surfaces. We're talking about billions of these rounded rocks. They cap the top two planation surfaces, as you see here in the right here and in the green. And here's other locations of quartzite. They're capping these surfaces, and the nearest outcrop of these is central Idaho. They don't outcrop on the plains. They've been transported long distance. In fact, where they're located is west of the Continental Divide, and we're east of the Continental Divide here. So normal rivers didn't do this. And this is another formation below the glacial debris in Saskatchewan. It's called the Empress Formation, and much of it is quartzite. I think you can see Saskatoon somewhere in there. And anyway, Prince Albert is up in here. This is central Saskatchewan. And you find the quartzites, nearest source, central Idaho, clear over there. They're also down over in here in southwest Manitoba and north central North Dakota. This represents a transport of about 800 miles from the nearest source. 800 miles. Wow. No normal rivers is going to do that. And in southwest Montana, where I live, and northwest Wyoming, we have some huge accumulations. I'm just going to point out a few of them. This big round area right here, that represents 15,000 feet of rounded rocks piled into a big crack in the earth, and the top has been eroded off. East and northeast of Jackson, Wyoming, right in here up to Yellowstone Park, just near Yellowstone Lake, represents 11,000 feet of rounded rocks all piled up. And now they're the mountains. In fact, some of them have names like Gravel Mountain. You can see a cliff of quartzite conglomerate up on a cliff, 1,000 feet high at Gravel Mountain. It's 11,000 feet deep right now. And according to David Love, 80% of it has been eroded. I believe him, because when you pile up quartzite that deep, you form unique marks on the quartzite, and you fracture the quartzites. See, I get one like this, and I hit it with all my might to crack it. I can barely crack it. It's so hard with a rock hammer. But down current from these big quartzite locations, I can pick up a quartzite. It has fractures in it and pressure solution marks. I'll show you pictures here. I can tap it with a rock hammer, it just shatters in my hand because of the high pressure of rock piled on rock has fractured these things. And here we are at the top of the Teton Mountains. There's 4 mountain ranges where you find them at the tops. I showed you 2 that are in Oregon. There's one in Montana called the Gravelly Range, where you find big ones like this. I was just up there 2 weeks ago. Anyway, this is the top of the Teton Mountains. There's 2 mountains up there that I think are remnants of planation surfaces. And one of them is probably an exhumed one, like Mount Moran. This is Red Mountain. We're about 10,200 feet. And we find rounded quartzite. Some of these are split vertically, and I think it's because they were fractured from that deposit just to the west. Anyway, these are some of the quartzite. You can see the pressure solution marks. Those aren't percussion marks. They're caused by rock against rock, and they recrystallize where the contact is because of all the weight of quartzite piled. This is the texture of the quartzite. It's a metamorphic sandstone. You can see it's kind of glassy inside. That's the texture of what it looks like inside, and that's found on the top of the Teton Mountains. This is the largest rock I found on top of the Teton Mountains. This mountain happens to be limestone, so you see some of the limestone angular rocks here, but here, not well rounded by water on top of the Teton Mountains. Now, I don't believe these rocks skipped up over these mountains. I believe this is telling us a lot about tectonics late in the flood, in that these quartzites were spread over a generally level surface, and then the mountains carried them up. And then valleys went down, and they piled up deep in these valleys. So we see tremendous evidence for the catastrophism late in the flood. And here's one on the top of the Teton Mountains with percussion marks, semicircular cracks in there. Some of these quartzites have hundreds of percussion marks on them, indicating very turbulent flow. Here's my summary of the quartzite spread long distance. And by the way, this is not an unusual signature. I've checked it north of the Alaska Range in Alaska, around the Appalachians. Also, I had an article in the Journal of Creation on the south central mountains of Asia. It's, the same similar variables, but also different variables. So you see different features around the south central mountains of Asia. But anyway, on the east side of where they outcrop in the western Rockies, they're spread 800 miles from their source. And they're also west of the divide at the moment. Well, these are east of the divide. They're spread 400 miles west, clear to the Pacific Ocean. Like around Willapa Bay, Washington, there's quartzites. The percussion marks indicate torrential, turbulent flow. By the way, it is very rare for percussion marks to form on quartzites today. I believe I've heard about it, but I don't think it's very often that it happens. The fact that you have hundreds of them on one rock and lots of them is powerful evidence for the runoff of the floodwaters. So in summary, major features of the Earth's surface can be readily explained by the retreating stage of the flood. Now, Taz calls it the recessive stage, but I renamed it. I don't know. I can't remember why I did that, but anyway. Massive erosion leaves behind tall erosional remnants, planation surfaces, and long transported resistant rocks. All the softer rocks were pulverized in the process. The eroded sediments form the continental shelf and slope. These are just a few of the abundant evidences that the receding water during Noah's flood shaped the Earth's surface. Mainstream geologists have great difficulty explaining all these features with their slow processes over millions of years. They have lots of ideas, and I've gone through their ideas, but they don't have little, if any, evidence for any of their ideas. All these features are worldwide, indicating a global event, not a local flood. This supports one of the most rejected historical accounts in the Bible, namely the Genesis flood. Therefore, we can trust the whole Bible as God's Word. Thank you.